those news articles. I just get the tech ones for some reason.
And that's fair. Welcome back, everyone. And we are live. Everything looks good.
Yeah.
Let me just double check over here. Oh, there it is. Okay. Yeah, looking good. All right. Let's get going. Welcome back to Silicon Scoop, everyone. With me, as always, is my co-host, John Irwin. How you doing this September 2nd, John?
Good. How are you?
I'm doing fantastic and ready to get back into the swing of things of work. Yeah, I had so many meetings I scheduled last week canceled just because people were away, and it's like I should have known better, but I tried.
Yeah.
But let's jump into this. We got a lot to talk about today, and we're back talking about quantum. Today, it's a genuine breakthrough where Japanese researchers use quantum entanglement to make robots move smoother, smarter, more precisely, cutting posture error up to 43% with a hybrid quantum classical controller. Let's talk about what this thing is, why it matters, when it's coming. What's going on here, John?
Yeah, so they use quantum computers to make, so this is robots in quantum, right? So it makes more robots move more smoothly and accuracy. If you think about it like they're upgrading the robot's brain from a regular calculator to a supercomputer. And so the problem that they solved was, so when robots need to move their arms or bodies, they face what's called the inverse kinematics problem. So it's like asking, if I want my robot's hand to touch this specific spot, what angle should each joint be at? So for complex robots with many joints, like humans have 17 joints in that for them to move to get to that. It becomes really, really difficult to calculate quickly and accurately. So the breakthrough is that they figured out how to represent each robot's joint as a qubit and use quantum entanglement, where quantum particles, you'll love this word, mysteriously influence each other to mirror how real robot joints naturally affect each other when they move. So this reduced calculation errors by up to 43% while using fewer computational steps. So why does this matter? Because it could lead to robots that move more like humans. So fluid response, responsive, and able to handle complex tasks in real time without that jerky, simplified movements that we see today. So my thoughts, Craig, I didn't know that it was the lack of computational power. I thought it was the lack of the actual muscles and things like that made them jerky and whatnot. What are your thoughts on this?
Yeah, once reading into this, it was pretty enlightening. You know, a humanoid robot with 17 joints creates an incredibly complex calculation problem that, you know, that having a hard time understanding. You're walking, and if your arm's so far forward, what does that do to your balance? And you got to calculate all this stuff, the things that we do automatically. So apparently that it becomes computationally challenging, and that's what's causing this herky-jerky motion.
Yeah, which I thought it was more. I didn't think it had anything to do with the actual motors and stuff. I thought it was more the lack of muscles for that fluid movement, if that makes sense. So if that's the case, then although remember that video that we saw with the muscles and the robot jerking and stuff like that?
Yeah.
Yeah, this is interesting. It kind of blew my mind when I read into it a little bit more.
Yeah, you know, that robot freaking out when it was on a thing, we have no idea what was going on there, so it's hard to judge that because it could have been trying to find its balance. It's used to standing up,
yeah,
and now it's hanging on something. You turned it on until the balance, and it's trying to figure out, you know, and then it glitches out and gets an error and starts, you know, doing whatever. It's not. What it looks like is it's trying to kill somebody versus it, you know, a natural computational issue. To me, I mean, quantum seems like a leap to solve how smooth a robot walks and can pour drinks and stuff like that. So
yeah,
we've seen the robot marathon, we've seen a bunch of things. I guess what this allows is robots to sync in unison as well, more to know exactly where the other one is and that kind of stuff at a computational level, so they don't interfere with each other in a close environment. And I guess it makes it computational. The qubit-based representation fundamentally changes how robots process movement calculations. So instead of calculating each joint independently and then combining them, quantum systems can process interconnected joint relationships simultaneously. So the quantum, so like when it naturally affects the elbow and the wrist. So for example, when a shoulder joint moves, it naturally affects the elbow and the wrist. And quantum entanglement can represent these relationships more efficiently. So it's great if we have quantum computing working and whatnot, but and a 43% in posture errors versus conventional methods. And I don't know, does that seem like a big leap to you?
I would think so, because like you're converging two transformative technologies here, right? So this is all like, so the research indicates that quantum algorithms could address multiple robotic challenges, not just the movement, but path planning, sensor data processing, like you said, multi-robot coordination, and decision making under uncertainty, which is interesting. But so again, we don't fully understand quantum, and we kind of do, but we don't. And you and I have covered quite a bit. But the cool thing about this approach is that, and this might seem ridiculous to people, but the quantum approach, it only requires 1 qubit per robot link. So it makes it feasible for the current, what we talked about this before, but the noisy intermediate scale quantum, which is the NISQ devices. And so a humanoid robot with 16 links would only need 16 qubits. And that is kind of well within our current hardware constraints that we have, right? So like we talked about a couple times, the circuits demonstrated, the quantum entangled circuits demonstrated up to 43% error reduction compared to non-entangled approaches. So this suggests that the methods could enable, like we talked about, real-time robot control for complex multi-joint systems. So it's more of a representation of how human neural networks control complex movements, which is going to help us in the future. But yeah, I'm still curious as to how they've implemented quantum entanglement with these robots to use it for their movements, right? Because it doesn't dive into like the real nitty-gritty.
Well, quantum entanglement mechanism works by creating qubits that represent joint position. So because standard computing is binary, it's on or off, qubits can represent things at a mere final level. They can represent multi-states of being. So a qubit that represent joint positions or orientation as interconnected quantum states. When a parent joint moves, the entangled qubits automatically reflect this movement in the child joints throughout the system. This quantum representation processes complex joint relationships simultaneously rather than sequentially, which is great. But I guess your question is, how are they physically implementing this into the?
Yeah, we know the theory behind it, right? That it represents points in a 3D, like the qubits can naturally represent points in a 3D space through their state vectors. The forward kinematic calculations are performed using quantum circuits, and each qubit encodes the posture of its corresponding robot link. And each position calculations involve measuring the expected values of the qubits with respect to the XYZ rotation gates, and then multiplying by the physical link lengths. But I'm curious as to, yeah, you're right. How are they physically doing this?
Yeah, and I commented on the 43% error rate reduction doesn't sound like much, but I guess without a base saying it's 90% accurate, now we're going 43% more accurate or what have you. we don't, understand what we're moving there, because they say 43% more accurate. It sounds like we still have a long way to go, rather than we're really honing in on the last 10-20%, which takes the hardest, right?
Yeah.
And thinking about it, things like this will allow potentially things like remote surgery, where things will have a extreme fine movement with robotics and stuff, versus any delay or herky jerky motion when you're talking about that kind of stuff would ruin the potential outcome.
Yeah. And my question is, where is AI in all of this?
Yeah, I guess that is a very good question. I guess the problem is AI is computational. So
Yeah.
if you feed it all this stuff, it's still trying to figure it out. So I don't know if that will make any sense.
Yeah. I'm guessing that they're using AI in their research and as they're developing this, but I was curious that as to, like, when we talk quantum, we don't really talk AI. We have a couple times, but we haven't talked AI when it comes to quantum too much.
Yeah, okay, let me separate this. I think AI is involved in all this. AI is telling the robot how to move, where to move, and doing the calculations and saying, okay, I'm going to you're got to go over there. There's stuff in the way, so I've got to walk around these 3 things. And then I don't know how fragile it is, so I have to check the tensile, whatever. That's AI. But the actual bot moving will have to be reflected at the quantum level, right? And you would assume that the AI would say, move forward 10 feet. It wouldn't say, move 1 foot forward 6 inches, lift it up, put it down, blah, 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 that it would hand it off to a system that understands the movement, because as we all know, AI is slow. So we want AI to do the stuff that is required to do that. And anything you can do in code or something else is just like, okay, you want me to move 10 steps? Great. And we'll just have the AI detecting if there's a problem, if I need to stop, or if I need, alerts and that kind of stuff.
Yeah.
So I like this concept, but we don't know. There's no pricing yet. Early access likely via cloud simulators and hardware partnerships, and enterprise R&D pilots will be bundled with software. And this is fresh research as of August 25th, 2025. We're validated on similar and 64 qubit hardware. No commercial timeline yet for any of this stuff. So
yeah,
very interested.
What I had read was, I think, 5 to 10 years, but again, that's typical. So that's typical timelines that we talk about, right?
Yeah. So 5 to 10 years for what? Quantum in robots, or 5 to 10 years for us to have regular robots running around? Like, we have robots.
So 5 to 10. So experts are suggesting 5 to 10 years for practical quantum robotics applications emerging.
Yeah, and it looks like the answer is going to be a hybrid of the quantum and traditional systems to make everything work together properly. So I'd love to hear what you think on this. Quantum won't replace classical control. It looks like it's going to augment it, where relationships matter most. The next wave of robots won't just compute faster. They'll move faster. They'll move better. So stay tuned. As pilots roll from labs to factories, hospitals, and homes, we'll be there to cover it. Thanks for listening and watching. Black metal solar. I can do that. Perfect. Today we're unpacking a wild solar breakthrough: black metal stegs, tiny generators that turn heat into electricity. Just jumped 15 times in efficiency. Let's talk about what it is, why it matters, and how you'll soon see it, and where founders can build real products around it. Let's talk about it. What is this, John?
Yeah, so this is cool. And 15 times is huge because, as we know, solar power is not that efficient, right? So researchers at University of Rochester made a solar device that generates 15 times more electricity than previous versions, using what they call, quote unquote, black metal technology. And this isn't your typical solar panel. So let's get into the nitty-gritty. So the core innovation lies in them using a femtosecond laser pulse, which is ultra short laser bursts lasting just 1/4 of a second to transform ordinary tungsten into a highly selective solar absorber. So the researchers tested different metals. They tested nickel, they tested copper, aluminum, and tungsten with varying laser parameters to optimize the performance. So the optimized tungsten selective solar absorber, or W-SSA, that exhibited good solar spectrum and weighted at an absorption of 0.9, which I looked this up. It's about 3 times higher than a bare kind of ceramic absorber. And it also maintained an infrared emissivity nearly as low as untreated tungsten. So why this matters. So this could power sensors, wearable electronics, remote devices that need reliable, maintenance-free energy. Unlike solar panels, STEGs can work with any heat source and don't have any moving parts, which makes them perfect for harsh environments. This is cool. I like their approach here. So what are your thoughts on this, Craig? Do you think this is the next step in solar energy?
Yeah, I really like this. I mean, I don't know yet whether this will be the next step in solar energy, but it's definitely an addition. These solar thermoelectric generators, the STEGs or the STEGs, they use laser treated black metal to absorb sunlight as heat, so they won't be nearly as reflective as some of the stuff they use now, which is interesting. There's a lot of, and like we've got a breakdown on torontostarts.com, check it out. But there's the hot side enhancement, there's the heat trapping mechanism, and then there's the cold side optimization, where it's laser etched aluminum heat sinks featuring nanostructures that double as cooling performance. So that these enhance service improvement and radiation, because it's the difference in the heat that this stuff measures, right?
Yeah.
Any time we can boost our solar efficiency, I'm on board, because we don't quite have the efficiency that's working as well as we want. Let's just face it. And we need better solar and wind technology if we really want more large scale adoption, because residential solar panels achieve roughly 20% sunlight to electricity conversion. However, photovoltaic systems use only certain light wavelengths and waste significant thermal energy.
Yeah.
So using the photovoltaic and the new STEG 15 times more efficient, but combining them, you're going to get even better.
Yeah, and there have been, in the last year, there have been some solar technology advances, like the perovskite tandem cell records, the commercial panel efficiency, and the flexible and transparent solar. So there are other ways, but those haven't really achieved the efficiency that they have with the STEGs. So, but the cool thing about this is the team's approach that they're doing kind of addresses key commercialization challenges by using single-step laser processing instead of a complex multi-layer deposition technique. So the technology itself could be used to power wireless sensors, like we talked about, for the IoT, fuel wearable devices, and service off-grid renewable energy systems in rural areas, which is interesting. So based on what I've read and based on what I researched, this has commercial viability relatively soon. Is that what you took out of this?
Yeah, I had this. Let me look at how much you learn, main concerns. It's lab stage now with promising, expecting near-term pilots, IoT wearables, and broader products, typically within a couple of years.
Yeah.
So once their ability and manufacturing scale are proven, we should see them.
Yeah. And like just some numbers that just to kind of reiterate the numbers, 80% solar absorption efficiency with the black metal technology, 40% reduction in convective heat loss with the greenhouse chamber, and 180% increase in cooling surface area with the microstructured aluminum, and also 25% weight increase for the complete system. So that's not the best, but as far as the other increases that you're getting, I think that's a good trade-off.
Now, did you read anything about hot or cold climates for this?
I didn't. Did you? I didn't find anything on specific hot and cold climates.
No, I was just kind of going through to see, because of the way it does it, I wonder, would we get as much electricity in, say, Canada in the winter on a bright sunny day versus, say, somewhere else?
Because it uses heat differential, right?
Yes.
Yeah. So yeah, that's a good question. The cool thing about this is that it's maintenance free. So being up in like the north is probably good for it. But as far as the technology itself and how well it would work in extreme environments, I don't know. That's a great question to ask. That's a great problem that they might run into that they'll have to solve.
Yeah, and durability is one of the things that's on the list to solve. So we'll have to wait and see, but I'm really interested in where this is going. Anytime they can improve solar panel, I'm in. Anytime we can get better technology around this stuff, like I'm not there yet, but we're getting there. Like you know what I mean when we're talking about renewables of 20% plus this, plus that. Once we're getting to 40, 50%, now you're starting to talk about a real solution that can convert energy. We still got to update our grids and update our policies around what we do with the energy coming from homes. Because at first you were able to tap into the grid and feed back any extra electricity, etc., and get credit for that. Now most places don't allow you to do that anymore.
Yeah.
So hopefully they get kind of that sorted, because with your peaks and valleys, otherwise you got to have big battery storage for a lot of stuff. And so anyway, this is great technology. I love where this is going. Any last words on this, John?
No, we'll have to cover this to see when it gets commercialized.
So photovoltaics turn sunlight into Internet of Energy. Black metal stegs could be its edge servers. Quiet, tiny, everywhere. Keep your eye on the hybrid PV plus steg devices in real world devices soon. We'll do that one last if we do anything. Season's out of sync. Okay. It's funny. I've been talking about this for a bit.
So have I. This was interesting because like I've been wondering about this. So
yeah, it's good. I'm excited. Let's dive in it. Welcome to Silicon Scoop. Today we're unpacking a big rethink. Satellites show Earth seasons don't stay in lockstep. We'll decode what that means for biodiversity, farming, coffee, conservation, cities, and your daily life. Let's get into this, John. What's going on here? How can Earth seasons not be the same?
Yeah, so what the scientists discovered was by using 20 years of satellite imagery, they created the most detailed map ever of how Earth's plant growth cycles vary across the planet. So their surprising finding, the neat, predictable seasons that we think of, spring, summer, fall, winter, they're actually far more complex. And in many places, they're completely out of sync with neighboring regions, which is crazy. So the key insight here is that we've essentially been thinking about seasons too simply. But caveat here, while it makes sense in places like Northern Europe or Canada, where you have clear-cut growing seasons, this textbook view breaks down in Mediterranean climates, tropical mountains, and arid regions where seasonal patterns are much more subtle and complex. So there are what's called hotspots of seasonal chaos, where the research identified specific regions around the world where seasonal cycles can be dramatically different and just short distances apart. So imagine Phoenix, Arizona, which gets both rain in winter and summer, compared to Tucson, which is just 160 kilometers away, where most rain comes from summer monsoons. So these differences, they actually create completely different growing seasons for plants, even though the cities are only a couple hours drive apart. And one of the most surprising discoveries is that all 5 Mediterranean climate regions worldwide, which are California, Chile, South Africa, Southern Australia, and the Mediterranean itself, they show what's called a double peak pattern, where forests peak in growth about 2 months later than other nearby ecosystems. So why does this matter, right? Why are we getting into this? So it's not just academic curiosities, because they affect everything from when coffee is harvested in Colombia, where farms separated by a mountain range can have cycles as misaligned as farms on opposite sides of the earth, to the evolution of new species, since animals and plants with out-of-sync reproductive cycles are less likely to interbreed. So what's crazy is that, like, there's, and it makes sense to me, this research and the outcome. And I don't know about you, but does this make sense to you, Craig, based on what you read and based on the article, that like this does make sense how this is happening?
It makes sense, yeah. And we just, to emphasize why it's important, timing drives ecosystems. So out of sync seasons change pollination, they change migrations, like you said, they change the food webs, they overlap with biodiversity hotspots, and they reshape conservation and agricultural planning. Like I've been saying for a while that, what we are experiencing here in, Southern Ontario in the green belt, I guess, is seasonal shift. If you look it up, there's been a gradual shift about a month in the seasons, so that winter starts about a month later, spring starts about a month later, everything's starting about a month later. And there's this whole science on it. Now we start going back and say, oh, okay, so maybe we're just out of sync, because now we got a little bit more why this is happening and why we care about it. So how will it potentially impact our life in the future? We could expect more precise local planning, farming, harvesting calendars, smarter water use, better wildfire and pest timing, and even regional product differences. Like you said, coffee harvesting based on all this.
Well, so I got to bring this up, though. Every season is off by a month except for fall, when fall comes early.
Yeah, it feels cold today and for the last week, but it'll get hot again, and we'll be like complaining about how too hot it is. It's just the way it goes. So when will we see this kind of thing? When can we understand this? The maps and animated explainer are available now. Agencies and platforms can integrate them immediately into their dashboards, advisories, and planning tools. So this visualizations are public. The paper may be paywalled, but the core satellite data, MODIS and Sentinel, are free. Implementation costs depend on your tools and your team. So almost anybody can go take a look at this.
Yeah, and my question that I asked and I got an answer from is this caused by climate change, right? So climate change is actually accelerating some seasonal mismatches, but the underlying patterns of seasonal asynchrony are actually natural phenomena that have existed for millennia. So climate change is making existing patterns more extreme and also creating new ones, which is interesting to me. I thought a lot of this had to do with climate change, but kind of not really. But if that makes sense.
Yeah, my research had suggested, and again, this could be just the way people like to approach it, increased seasonal asynchronicity, related because of climate change. So this stuff has been going on for a while, but it's worse now. But we've only got 20 years of satellite data, so I don't know, how, is that a long enough study to know? And do we have the actual data on?
I don't think
how worse it was. We had 10, diverse regions in this area now. Now we have 20 that are different. Just curious as to, what those things are. But as we understand our world and our planet, and we're learning more about water currents, and they didn't work the way we think they are, and these don't work, seasons don't quite work the way we think they did. And the more we get to know our planet, the better we can coexist with it. Like you said, farming seasons, understanding locally what's going to work and what isn't going to work, using this information like coffee, like you said, there's so many crops, among other things, that will pollination, tracking the migration of the bees and whatnot, that can be affected by this and now tuned up, and we can get a way better idea of what's going on.
Yeah, exactly. Like understanding these patterns is going to be crucial for predicting wildfire seasons to managing protected areas. So like they need to re-strategize and account for this complexity in these regions for sure. What I thought when I was reading this was I thought they were going to talk more about, because I thought they were going to talk more about the globe as a whole, which surprised me that they said it's less, Canada's less affected, which kind of blew me away because, well, maybe we're just in this bubble here living in Canada, but I thought that we were shifting quite a bit too, but it kind of, and this is what I got out of the article, but it kind of said that Canada is not as affected as other climates.
Yeah, I got that as well. And again, I don't know what that means. What we're not as affected of other clients. And again, because the research is behind a paywall, we could only rely on some third-party information. What do you mean we're less effective? We're 1% less effective. We have only X more biodiversity regions as a result. Because we have the Canadian Shield, that whole region is affected a certain way. There's a number of ways you could address it, but what does it mean? Like 1%, 2%, 10% less, more? Okay, we're not affected the same.
Yeah, exactly. How do we quantify that?
Yeah, does that mean everyone else is in trouble and we should be jumping for joy? Does that what does that mean? That's why
everyone be moving to Canada. You're protected. Yeah, exactly.
So I love that we're tracking this stuff, and the more we learn about biodiversity and understanding the hotspots and how seasonal changes affect locally, the more we can plan for extinction of species and plan to care for them better, or migration. Oh, this thing's moving, so we expect these species to move, or any number of things. And it's really having this information is a big leap forward. And then when you start feeding this stuff to AI and whatnot, we're going to get better understanding of crop cycles down to like the days and hours versus what we used to have on a very local level. And I'm very interested in what the future holds for this.
Yeah, me too. Yeah.
So apparently our seasons didn't change. Our map did. With timing and focus, we can protect biodiversity, grow smarter, and adapt faster. Subscribe and share, and let's turn data into action. And let's keep studying this stuff. All right. Some of my outros are better than others.
Yeah, they're better than they have been.
I'm trying.
Yeah, they're getting better. Yeah.
All right. Let's talk about one of the most exciting medical breakthroughs in decades: growing new human teeth. That's right. A Japan-led team is trialing TRG-035, a drug that lifts the brake on our built-in tooth growing program by blocking a protein called USAG-1. We'll break down how it works in plain language, who could benefit, safety, timelines, costs, and exactly what you should know to prepare. What's going on here, John? Growing teeth.
Yeah, this is cool. So let's start out with this could potentially make changes within 5 years. So the basic problem that we're talking about here is, unlike bones, which they can actually heal and regrow themselves when broken, teeth are actually the hardest material in the human body, but completely lack the ability to self-repair. So once you lose an adult tooth, that's it. Your only options have been artificial replacements like dentures, bridges, or implants. So the breakthrough here is that they discovered that humans actually have the biological blueprint for a third set of teeth hidden in our mouths. Dormant tooth buds that never develop because of a protein called USAG1. It acts like a biological off switch. So this protein, it blocks two crucial growth pathways, BMP and WNT signaling, which are essential for tooth formation. So the solution they came up with was a special monoclonal antibody that neutralizes the USAG1 protein. So when they use this biological key, it unlocks the dormant tooth buds. And so the body can naturally grow new, fully functional teeth with proper roots, enamel, and integration with surrounding tissues. And it's actually simple how it works. They inject intravenously the treatment, and it deactivates USAG1, which allows for the dormant growth development pathways to reactivate. So in animal studies with mice and ferrets, a single dose was enough to generate complete functional teeth, which is absolutely crazy. What are your thoughts on this, Craig? Do you think this is the end of dentists?
Well, I don't quite think it's the end of dentists, but we might be looking at the end of implants.
Yeah.
Because, you know, you got a cavity, we want to potentially do the work. It doesn't fix the tooth. So you can just pull it out and trigger a regrowth of a tooth, though. So, you know, you want to just fill in the cavity, but once you take it so far, you're like, screw it, pull it out. Let's pop in whatever that triggers this TRG 035 and trigger your teeth growth. If you can target it to a specific bud, awesome.
Yeah. So my question is, so in this article, they said a third set of teeth, right? What happens if you mess up the third set of teeth? Is there no fourth set then? Like, can you just turn off the USAG1 and grow a fourth set if you have to? That's what I was wondering.
I don't know.
Yeah.
Let me take a look at that. Let me research
sorry, I
that
didn't
one.
mean it like, oh, do you have the answer to it? That's a question that I was having about this article. Because they keep talking about this third dentition tooth bud, right? So does that mean that once the third dentition is activated, you can't? There's no fourth one. That's it. So that was kind of mine. And so timeline talking about this is, so if phase 1, it's the safety trials with 30 participants aged 30 to 64 succeed. Then phase 2 will test efficacy in children's aged 2 to 7. So success would represent the first time in human history that we can naturally regrow lost teeth rather than replacing them with artificial substitutes. So again, who's going to benefit from this, right? This is essentially anyone who's missing at least one tooth. But I think right now, based on the article, the primary target is children born with congenital tooth agenesis, which is a condition which affects about 1% of the population who are missing multiple teeth from birth. And eventually, it could help anyone who's lost teeth due to decay, trauma, disease, whatever.
Yeah, so they've conducted the first in-human studies in adults missing at least one tooth. Current phase 1 trials in Japan. So it looks like human possess latent potential for multiple dentions, analogs to shark continual tooth replacement process biology. So I'm doing a deep dive here. It seems to indicate that we might be able to do continued growth.
Okay.
But we'll have to see. So quality of life declines with tooth loss. It affects nutrition, speech, facial structure, and psychological confidence. You know, tooth decay and stuff with your mouth is a big cause of gut disease and other heart disease and other problems. So having stuff where you can regenerative dentistry like this is a huge step in the right direction.
Yeah, like essentially losing a tooth might become as temporary as getting a cut on your finger. And I love this because that means I can eat all the sugar I want, not brush my teeth, and just go get a new tooth or a new set of teeth.
Okay, so I did a deep dive here and say, no, we are diphodont. By design, we have 2 sets of teeth. Research suggests a possible 3rd generation is what we're talking about. Can be coaxed from dormant tissue in some sites. There's no evidence of a natural 4th or ongoing infinite set in humans, just to be clear.
So okay, so I can't eat all the sugar I want and not brush my teeth. Like, I only got a 3rd backup set.
Yeah, but what this is interesting too. So if you can hold off long enough, like on implants and whatnot, this technology, new teeth timeline could be 2030. This could be available. So
well, at least I can take advantage of the tooth fairy once more and get a 3rd set of teeth.
Yeah, I'd be curious. That's what I'm saying is instead of getting dentures when you're old, maybe you could just, okay, let's regrow all my teeth when I'm 70 and be done with it.
Yeah. I wonder what a tooth is going for with the tooth fairy these days. $20, $50?
I don't know, but expect this to be expensive because, when these things start out, early biologics tend to be expensive. Coverage and pricing will depend on insurers and regulators. Expect costs to fall over time once it's widely adopted. So they'll probably have to reflect the cost, like what's the cost of this versus dentures or for the fake teeth and whatnot. So it'll be interesting to see where this goes, but they are talking within the next 5 years that you'll be able to do this, buying, obviously approvals.
Yeah.
So what do you think about this? Do you think you'll be jumping in and getting new teeth, or regrowing your own teeth could shift dentistry from prosthetics to true regeneration? So we'll keep track of safety, access, and timelines as this stuff comes up. So if you found this useful, share it, tag a dentist friend, drop questions. We'll leave answers in the comments, and we'll keep track of this. So follow us, and next time there's an update, you'll be one of the first to know. All right. All right. So I'm going to let you say this word once we get started because
Malibdinum.
What's it called?
Molybdenum.
Malibdinum.
Molybdenum. Yeah. Sorry, go ahead.
All right, I'll hand it over to you just as we get started to say the word because I'm going to struggle, obviously. The wild new trick that lets a single atom of a thin material. What's this material called, John?
Malibdinum disulfide.
Or MOS acts like a semiconductor, a metal, a superconductor, or an insulator just by steering potassium ions with a custom transistor. Think software-defined materials where voltage, not a factory, flips the physics. What's going on here, John?
Yeah. So, this is cool. So, like the scientists have achieved with molybdenum disulfide, this ultra-thin layered material that can act like 4 completely different electronics. So, it can act like a semiconductor, which is like the chips in your phone, a metal to conduct electricity, a superconductor to conduct electricity with zero resistance, or an insulator to block electricity. So the core discovery here is that they demonstrated unprecedented control over molybdenum disulfide's electronics properties through potassium ion intercalation. So let's call it MOS2. Sub 2 naturally exists in 2 structural phases. So the 2H phase and the 1T phase. So researchers built a field effect transistor, or a FET, device that precisely controls potassium ion insertion between the material's atomic layers. So the phase transition occurs at a critical threshold of approximately 2 potassium ions for every 5 molybdenum atoms. So that's crazy. it triggers an abrupt structural transformation from 2H to 1T phase. So what makes this discovery extraordinary is that by fine-tuning the potassium concentration and temperature, they can achieve 4 distinct electronic behaviors from the same base material. This blows me away how this can work like this, right? What are your thoughts on this, Craig? Do you think this is like straight sci-fi? Do you think this is cool? What are your thoughts?
This is really cool. This is definitely straight sci-fi.
Yeah.
And it's hard to get your head around when you start really thinking about, you know, a reconfigurable material could replace several fixed parts, channels, interconnects, isolations, even cryogenic links, simplifying designs and enabling adaptive on-demand performance. Like long term, think about better research tools, or near term sensors and niche cryogenic systems. Longer term, think about thinner adaptable electronics that reconfigure for, I don't know, battery life, speed, or security at runtime. So we're talking about some amazing types of technologies and things you can do when the material, what it acts like, is your choice.
Yeah. And so beyond scientific interest, right? This discovery, this is what I like about this. It opens pathways for neuromorphic computing devices that can reconfigure their function based on computational needs. So traditional electronics, obviously they require different materials for different functions, but this approach enables a single material device with multiple operating modes. So also, because we love quantum, this work also advances quantum device engineering, because where different electronic phases could be spatially patterned on the same chip. So for example, superconducting regions could provide lossless interconnects, while semiconducting regions handle logic operations all within the same material, which just is absolutely nuts. Again, this is like, how practical is this? We're still in early research phases. So the technique uses standard semiconductor fabrication methods, but the main challenges are operating temperatures, which I think it's like in the kelvins, and scaling to larger devices. But the principles could lead to room temperature applications as we better understand the physics.
Yeah, so superconductivity requires deep cryogenics of negative 268 degrees Celsius or so.
Yeah, so for this, the temperature was set at 80 Kelvin or minus 193 degrees Celsius.
There you go.
Yeah, so, sorry, different phases, different temperatures. So
yeah,
the superconductivity in the 1T phase was at 5 Kelvin, so minus 268 degrees Celsius.
Yeah.
So we're ways off until we can get that room temperature working, but I think this is the right step. Now, could this replace current electronics? I would say rather than a replacement, I would think of it more like a complementary revolution, enabling new devices, new types of devices currently thought impossible with the current technology. So I think, and based on what I read, we're about at least 10 years, if not 20 years out from something commercially viable.
Promising progress of the wafer scale MOS exists, 2-inch monolayers right now, but uniform growth, transfer, and reliability remain hurdles. So transition to consumer devices likely years away, not months.
Yeah, like we're talking 10, 20 years. But that could be reduced as new scientific insights come, as we advance our understanding of quantum materials. That could accelerate this getting to commercialization phase quicker.
So go ahead.
No, go ahead. It's a lot. Like this is one of the more the more advanced tech that we've covered in a while, I would say.
Yeah, and you have to really get your head around the switch between a semiconductor and an insulator and a superconductor, and metal behavior versus non-metal behavior of the material, and the practicality of some of that is very interesting.
Exactly.
There's sometimes
because we've learned that like conductors and insulators are two completely different types of material. Like one can't be another, right? And so this is crazy. Not only a conductor, but a superconductor, which is zero. Oh wow, why can't I think of the word? Anyways, zero resistance. There we go. Jeez, it's too early. I'm excited for this, but again, I can't get too excited because we're 10-20 years out from anything. So, but I'm curious to know where this goes in the next couple of years, if it advances at all.
Yeah, and these breakthroughs contribute significantly to superconductivity research and next generation electronics. And the versatility of this MOS could lead to electronic components that adapt their properties based on operating conditions or user requirements. And you map this kind of thing to, we were talking about changing 3D interfaces where you could put your hands on the steering wheel or something and the buttons would form where your hands are, or you change a setting and a dial comes out of the glass. You can a dial you can turn or adjust or what have you, or that kind of thing. You pair that with this and you've got some very interesting, the shape can change, a lot of things can change about it, as well as what the device can do.
Imagine this with that. Remember that little robot that could morph or could melt? It was behind bars. It melted and moved out of the bars. Remember that?
Yes.
Yeah. Imagine mixing that with this.
Yeah.
I think now you've got the T1000. The T1000, is that the liquid one?
I think so. Yeah. The T800 is Arnold.
Okay, so yeah, the T1000, the liquid Terminator. I think that's where we're at if we combine the two.
So is this the future? Liquid Terminators on the way, along with Skynet and all quantum and AI, and this is the beginning of the end. If silicon was about shrinking transistors, MOS phase control is about editing reality on a chip, a voltage knob for matter itself. Continue to watch this space for more on this and see where this goes. We'd love to hear back from you.
Yeah.
All right. What do you got going on, John?
We made it.
We did.
Yeah. Nothing. Just plugging away, helping companies get government funding, Flowgrammer events, and Startup Drinks TO and Tech TO together, a bunch of events. So things are coming back now that we're in the fall. So this is exciting. How about you, Craig?
Yeah, things are getting going. We've got, one, obviously this is recording in September, so September 16th, but we've got Startup Investor Drinks and Flowgrammer events in October, November, and December scheduled. So check out Toronto Starts or torontostarts.com or flowgrammer.ca for those details. And we'd love to see you downtown in Toronto and at one of our events. And we'd love to hear back from you.
Yeah, let us know if you're coming out.
Yeah, that'd be great. And John, be a little bit more clear about SR&ED non-dilutive funding.
Yeah, so SR&ED is a tax credit. It's non-dilutive, but it's a tax credit, so you get your money back from eligible expenses that you spent. Non-dilutive covers both tax credits and grants, and I guess loans, because anything that doesn't take a part of the company, right? So you've got grants, you've got tax credits, and you've got loans that you can access from the government, which are all non-dilutive funding. So if you're doing anything innovative, or if you're looking to spend money, you got a project in mind, reach out to me on LinkedIn.
Yeah, and what I like about SR&ED is based on spending. You don't have to actually be making a profit. You just have to be spending the money.
Yeah, and there's some great changes coming through the legislation that got tabled. So if you want to know more, reach out to me. There's some really, really good positive changes that I hope go through. So, but if you need more than just non-dilutive funding and you need help with your business, where do they go, Craig?
Oh, they can check out torontostarts.com or startupcoach.ca. All the information is there. I help businesses who are stuck take to the next level, be focused on the things that actually move the needle and move them along. If you want more help on that, check out torontostarts.com and startupcoach.ca and book a discovery call and see how I can help you. Thanks, everyone, for watching and listening.
Thanks, everyone.